Good morning and welcome to the first online talk organized by the NIDU Research Project, funded by the National Research and Development Agency of Chile. This project is called Cyber-Physical System for Smart Mining, Industrial Electronics 4.0 and Data Driving Process Control. And it is a collaborative research in electrical engineering in the area of control and power electronics. The project is led by Pontificia Universidad Católica de Chile, the Andrés Bello University, and the University of Talca, in collaboration with 5 international universities and 6 mining-related companies. Today, we are pleased to have Professor Mark Sumner as a guest with his presentation on energy communities, help with the challenges for future electricity grids. Dr. Mark Sumner is Professor of Electrical Engineering System at Nottingham University in United Kingdom. Mark's research interests include the control of electrical energy system and power electronics. Recent research has explored the development and use of new energy management strategies for renewables and smart distribution systems. Professor Sumner, thank you very much for accepting our invitation. The microphone and the screen is all yours.
Okay, thank you very much for that kind introduction. I hope to talk about energy communities today, which may be a little bit different from the microgrid concept that you're probably familiar with, but it's an important part of the research that we do here in Nottingham. Before that, I just want to give a brief description of our research group at Nottingham, and then I'll describe what I mean by an energy community. So power electronics at Nottingham. I guess you've heard a bit about this from Pat Wheeler in his presentations that he tends to give in Chile. So I thought I'd just give a very brief overview. So I'm from a city called Nottingham, which is pretty much in the centre of Great Britain. It's a very pretty and a very busy city. And its most famous claim to fame is that it's the home of Robin Hood. And it's very easy to get to, not too far from London at all. More specifically, I'm from the Power Electronics Machines and Control Research Group at the University of Nottingham. We have a very big research group here that focus on all aspects of the design and use of power electronics and machines. And that can be drive systems and their control. It can be looking at power electronic systems and the integration of power electronics. It can be looking at reliability and health management underpinning making our power electronic systems and making them smaller and more powerful. And then we also have a look at a lot of different electric machine technologies as well. And these are for all sorts of different applications, whether it's transport, renewable energy, smart grids, or as we started off many years ago in the field of industrial drives. And we're lucky enough to be moving into a new home at the moment, a big new specially designed building for our work. It's going to be the home to about 180 researchers, academics, technicians when it's eventually populated. But we have specialist laboratories for doing research into power electronics, power converters and motor drive systems, and also a good or an excellent high power laboratory as well. So we have a lot of different areas of research going on within the group, and we're very proud of what we do here. So hopefully we'll be able to show you some of these facilities if you come to the UK in the near future. So moving on more specifically about my research, it's looking at community energy. So let's just give a bit of background about this. Move on to the next slide. So really the background, certainly within the UK, from a UK point of view, is that we've had a very big uptake of domestic generation, mainly solar panels. And this over the years has been encouraged by all sorts of feed-in tariffs, but also a personal ambition of many homeowners just to take control of some of their resources, in particular here, their electricity resources. Alongside of that, we're having a gradual move towards the electrification of heating and cooling systems and also transport. So we're starting to see many more electric vehicles on the road over the last year or so. And both of these are creating challenges at the distribution level. We're seeing significant voltage variation in some parts of the country. There's the potential for reverse power flow in our system, and this becomes very challenging for our power protection systems. And a good example of that is bottlenecks that we see in our system, particularly in the southwest of England, down in Cornwall, where the increasing use of PV systems domestically means that there are some severe strains on the system in that particular area of the country. And the distribution network operators have tried all sorts of innovative techniques to try and overcome those bottlenecks. For example, they tried something called the Sunshine Tariff to try and encourage users to use electricity during the daytime by saying that it was free during the daytime. So there are real challenges that we're having to face because of this increasing uptake of PV. And on top of that, the cost of PV is still reducing, but also we have domestic batteries coming into the market now and starting to be used. So people have probably heard of the Tesla Powerwall as one example, but there are all sorts of different manufacturers producing small-scale lithium-ion batteries that can be used at household level. And accompanying all of this, some of our market leaders are starting to introduce slightly different tariffs for the purchase of electrical energy. So those are also a motivating factor in the changing way that we produce and consume electricity. And accompanying all of this, there's a need from the network operators to address all of these challenges, but not by totally redesigning the infrastructure that supports it overnight. From their point of view, they see these challenges creating the bottlenecks, and they know they need to do things about this to change the system and to reinforce the system. But on a gradual basis, they would prefer to do it on a gradual basis rather than having to invest all in the space of a year or two. And this is potentially where community energy can help out. So what do I mean by community energy? Well, in our definition, it's a group of neighbouring dwellings, or it doesn't have to be residences. It could be schools, it could be shops, it could be all sorts of different energy consumers who have their own generation, who may have their own battery storage systems, but who are able to trade any excess power that they have in a hierarchical way. So they might want to trade with other members of their community. They may want to trade with some sort of central battery storage system. They may wish to trade with the main electricity grid. So the community energy is simply trying to facilitate this low-level trading of energy resources. Now, we don't need to operate as an island within this community energy concept. We assume that we have a healthy main distribution system. And this is all about encouraging better use or better energy usage profiles, which can help with maintaining the system to work in a stable way. And community energy exists. It's existed for a while now. So, for example, we've got at least two community energy systems within Nottingham. There's the Meadows community down by the River Trent, who we've been working with for a long, long time. And then Trent Basin, again, another community by the River Trent, is a new build establishment that I'll talk about a little bit later on. But these are both very good examples of community energy. So this is where the title of the presentation comes from. Can energy communities help with the challenges for future electricity grids? So what I want to try and illustrate is by working as collaboratives here in the way that we produce and consume electricity, it can be very beneficial to the way that our electricity system grows and progresses. So the aims of our investigation really are to investigate how allowing customers who can produce and consume electricity, if we can allow them to work cooperatively, will that reduce their energy costs? Will that improve consumption patterns as seen by our local distribution network operators? Basically, we're trying to do peak shaving here and reduce the strains seen by the grid. Can we avoid having system bottlenecks and allow even more local generation onto the distribution system and overcome the reverse power flow and voltage problems I talked about earlier on? Now, those are the technical ambitions, I guess, but understanding community energy also requires us to understand the financial rewards from it, the social benefit of it, and also the way to create a community energy system without requiring changes in householder behaviour. Things need to be user transparent, otherwise they may be adopted for a short time, but then they get neglected. So let's look at how we approach this problem. So we started off by looking at rule-based control systems. So let's have a look at how we apply that within community energy. And this graph is really trying to illustrate the hierarchical control approach that we want to have. So down at the low level, we have two energy communities where we've got, within a community, we've got local renewables, mainly PV in this case. We may have some batteries. We have the ability to do load shifting. And then also alongside of that, we have the natural consumption of the end users. And there are control actions generated by a local controller on the basis of references coming down from a higher level controller. And that higher level controller may be controlling two or more different communities and also other types of communities, so shopping malls or industrial establishments, for example. And the higher level controller interacts with the network operator, understanding the electricity market prices and trying to predict customer load, and also trying to predict weather forecasting, which is somewhat challenging in the UK, as you can probably imagine. So if we think about what happens in one of these communities, then really what we're trying to achieve is primarily to make sure power and voltage quality and stability at the lowest level are maintained. That's the key overriding aim. But at the same time, we want to manage energy profiles at the local level to the benefit of our consumers. And that can be using load shifting, demand side management, if you like. It can be using any batteries that we have installed. And in desperate situations, we may have to do some curtailment of renewable energy systems. So those are our control actions available. But what we're trying to do is to create a predictable energy profile, which can be of benefit to the wider transmission and distribution system. So ultimately, we have a consumption profile from our community that looks like this, but we can control renewables or home appliances for demand side management or local energy storages. And then we want to create a pattern that may look like this. The profile is not too important at the moment. The key thing here is that we're managing to reduce consumption for the peak time between 4 and 6 o'clock in this particular instance. But there are other profiles or other consumption patterns that you might wish to put priority onto. So using this rule-based approach, and here I'm just showing what can happen with a community of just simply 2 dwellings. So the original profile over a day and a half is the red consumption profile. So we can see that it's got a very low consumption profile overnight. During the day, the power becomes negative, which is indicating a lot of generation in these 2 households, which means that we are exporting a lot of energy back to the grid. And then as we progress through the day, we get to the evening peak. So the consumption profile is significantly higher here. In this, this is a simulation of these properties, and in this we've included an electric vehicle and a heat pump as well, in order to try to imagine what will happen in the foreseeable future. And when we put our community energy management system onto this, we get the blue profile. So what you can see here is that the export that happens during the day is significantly reduced, and we're capturing that energy by using demand side management and shifting loads to that time of day, or charging up a local battery system. The target that we're after in this case is very simple. It's the predicted average power for the day, and what we're actually after is hopefully a flat power consumption profile. So it's relatively simple in this case. Now, if we increase the community size considerably, so if we go up to 30 houses, then we scale up the consumption profile. It's looking roughly the same pattern with the evening peak here and with some less regeneration here, because there are 30 houses in the community now that are able to consume any excess PV generation during the day. However, if we then add on our community management system with the demand side management and the local batteries, we find that we get the blue profile, which is very much matching the target, which is the average power for the day. We have a little bit of discrepancy here, and we have a little bit of discrepancy here, but for the rest of the day, the actual power flow from the community is matching a constant target. So we've got this massive reduction in peak consumption here, which is one of the chief aims of what we're trying to do with this. We get this mismatch at 1 or 2 o'clock in the morning due to the load shedding algorithm. So we've deferred charging of electric vehicles for a certain amount of time, but they need to be charged at some point, so they're charged overnight. And one of the key findings from this actually is that when you do this analysis over a year for different size of communities and try and understand battery sizing for each of these communities, you see that the battery capacity that you need per household for the community sizes comes down considerably. So if you've got a very small community of 2 houses, in order to get best results, you need a capacity of 8-9 kilowatt hours per household. But as you get up to a community of 30 houses, that comes right down to about 3.5 kilowatt hours per dwelling. And then you don't get much additional benefit as you increase the community size. So this is really reinforcing the concept of community energy. If you can work together as a community, you can get some significant savings costs because you're cooperating and making use of economies of scale, and also making use of the fact that trading energy means that you can exchange PV energy without the need of batteries, just by simply having people consuming during the day when you're not. So this is just a fairly simple illustration of how community energy can create benefits, both in terms of the DNO and creating this nice fat consumption profile we saw on the previous slide, but also to the benefits of the end user, both in terms of their electricity cost and in terms of the cost of any additional infrastructure that they need. So the control algorithms that we implemented can become more sophisticated, so we can move on to predictive control. And I'm not really too interested in the detail here. It's just trying to use something that takes into account predictions a little bit more in a bit more of a sophisticated way, in order to optimize the system behavior while accounting for predicted changes in the future. And we found that the best way to operate is to have a dual layer system where the upper layer is a model predictive control layer, but the lower layer remains a rule-based layer that operates on a much faster time scale than the model predictive layer. So if you like, we've got the model predictive layer operating with a sample time of 15 minutes, whereas the real-time control down in each at the lowest level is operating with a sample time of a minute. Again, we're creating an energy management system. In this case, it's for a house, a single house, in order to improve energy costs, maximize use of local generated electricity from our PV systems, and smooth out fluctuations in power consumption. And if we have a look at what happens in this case, sorry, the graphs are a bit bizarrely laid out here. So the black line in this bottom left-hand corner represents the household original power consumption, and the red line is the generation from PV. So initially, we would see a lot of export from this system during the day. By adding a battery and some demand management or load shifting, And in this case, it's driven by a time of use tariff now. We can improve this consumption profile significantly. So up in the right-hand side, the blue dotted line represents the time of use tariff. So overnight, it's very cheap. It's 5 pence per kilowatt hour. During the day, it's up to 12 pence per kilowatt hour. But during this evening peak, it's 25 pence per kilowatt hour. So this really is an expensive time to consume electricity. And originally, the household would be drawing it from the main grid supply at that time. But with a local management system, we can change that profile such that all of the electricity pretty much is consumed from the grid overnight in charging up the battery. All of the export is correctly used in charging up the battery during the day. And then during the daytime, when the tariffs are higher, we don't draw any electricity from the grid at all. And in fact, we've done this with several tariffs. The time of use tariff that we have here, a thing called the tide tariff, is the best because it's very, very predictable. Real-time pricing is okay, but it introduces another level of prediction into the operation of our system. So in the test that we did, we couldn't make it better than time of use tariff system. And we can scale this up to a community. So again, we have a 2-layer energy management system for an energy community, whereby the community level now is the model predictive control, the optimization process, and it's sending out power references for each household. And in this case, the power reference is trying again to optimize energy consumption in terms of the time of use tariff and reducing energy costs, and also maximizing local power consumption, self-consumption, if you like. And in this case, the predictive control is updating the lower level every 15 minutes. And then the lower level is operating on a minute-by-minute basis within each household to control power within our system as well. And we're doing a combination of battery control and demand-side management as well. And this is the sort of thing that you see when you apply this 2-level community energy management system. The original consumption profile is this black consumption line for the community on the top, and the generation is the red. And by applying this energy management system to the community, we reduce the consumption during the medium and the high peak tariff times to 0 by using the battery and by using demand-side management. We charge the battery with any excess PV during the day and with low-cost overnight charging from the grid. And you can see we don't have a perfect battery because the battery completely discharges about this time here. So the grid consumption then follows what the community needs. And this is because the battery has been sized for a complete year. So a battery will never be ideal for every day of the year. In the winter, it has to be designed for predominantly charging overnight, and in the summer it has to be designed predominantly for PV charging. So there's a compromise in the sizing of our battery system, both in terms of its power capability and its energy capability as well. But in terms of a community level battery system, we can do it either as using batteries in people's household, or maybe there's a central battery system as well. And just to give you an idea of some of the costs that we can reduce in terms of consumers' electricity consumption, with this particular scheme, the whole community has a significant reduction of 11–12% when it introduces the centralized battery with battery control. And it works very, very well in terms of smoothing out the consumption profiles as well. So one last thing on the technical side, the sizing of the battery is incredibly important. And I've discussed that already in terms of the size per house. Now, we have done some work with real communities here. So when we work with real communities, we have to understand what they can do with a community battery. So ideally, they would use it to provide community energy management services like the services I've just described. But anything that they purchase has to be compared with if they could use it for capacity market servicing or other services to the main grid, such as firm frequency response services. So we've done an analysis comparing our approach to using a battery compared to the conventional approach of capacity market or dynamic firm frequency response. And without going through this in any detail, really what we found, and this all took into account battery degradation and the costs of using the network for moving energy around, the TUOS and DUOS costs. We found that if you wanted to use a community battery, and in this case, we've sized it at a megawatt hour and 500 kilowatts, and I'll explain why in a minute. If you want to analyze the behavior of that over many years, then if we use it for our community energy usage, then it would have roughly a 12-year payback period. If we wanted to use it for capacity market usage, it would take 13 years to pay back the initial cost. And if we could use it within the fast frequency response market, then that brings it down to a 10-year payback period. So that gives you an idea of what we're trying to do with a battery for community energy compares with what you would do with a battery in terms of supporting the national grid. It's better than some approaches, but worse than other approaches. But there is a minimum investment cost for fast frequency response services of half a megawatt. Okay, so the final thing I wanted to talk about is the fact that we've done this work with real communities. So this is a laboratory that I have where we can emulate household loads and communities as well, so that we can test out any equipment and any control strategies within a safe laboratory environment before employing it for real. And we can also capture data in real time for communities that we may wish to work with, and test things out within the laboratory as well. So, for example, for one project, we wanted to install a central community battery in this little household estate which we have on campus. And we were able to emulate the household in real time using power converters, and similarly emulate the PV array in the lab using power converters, and test the control of the battery management system. And then we can deploy it in real life. So that example that I talked about was a project sponsored by E.ON, which was implemented in the Creative Homes. But we've also looked through a project called Empower at implementing these technologies in a city, in a town called Bath, which is down in the southwest. And you can see the housing stock there is very old and produces its own particular challenges, especially associated with communications. But we installed demand-side management and batteries within these houses, and had about 15 or 20 houses working as an energy community there. We had special dispensation to do that. We also operated a very similar project in Nottingham called Sensible, under which is funded by Horizon 2020. And again, we managed to get batteries put into a local community in order to get them to experience these technologies and the savings that they could get from both having the batteries, but also using the batteries and demand side management as a community rather than just as single end users. And this is the Trent Basin project that is ongoing at the moment. It's a new build development in Nottingham. There's lots of PV in here, but it also has a community battery, 1 megawatt hour, 500 kilowatt hours, that was opened about 2 years ago. And it also employs demand side management. And we're looking to incorporate electric vehicle charging and usage within this community as well. And one of the key things to come out of the Trent Basin project is that we set up a community hub there to communicate about specifically the energy usage patterns that the community was creating. But it's actually become the central community hub for the community for all sorts of different social things as well. So it shows that people have an interest in this technology, and when they work together, it can help develop other community interests as well. So it's not just about the technology, it's about developing community as a whole. But these sort of things ask for more questions. The more that you try, the more questions that you ask. So we're now in the realms of the technology works, but there are other hurdles to overcome. So you have to buy licenses to be able to operate like this, and these licenses are incredibly expensive. We need smart meter deployment. The network operators need to be on board to operate this. We've got to take into account electric vehicles, and electrification of heating are going to be big things. And whoever invests in this technology will want a return on investment very, very quickly. 13 years is a long time for them. They would prefer less than 5 years as well. So as part of what we've been doing, we've been lobbying in Parliament. This is a Parliament day that Nottingham had, and I'm there trying to promote and ask some of the questions about community energy to members of Parliament here, to promote this as a growing technology area within the UK. So to conclude, I'm sorry, I've gone over time. The proposed community energy control can significantly reduce customer energy costs. I think we've demonstrated that in every project that we've run. It can certainly reduce peak powers that are seen by the network. From that point of view, it's beneficial to them, and reduce reverse energy power flow, because it increases self-consumption by end users. And because it can reduce power peaks, it can help with the incorporation of more electric loads, such as electric vehicles and electrification of heating. It's going to be of benefit to DNOs as they look to reinforce their grid in the presence of all of these new technologies. And it will also be of benefit to end users who invest in this technology, because it can reduce their energy bills. And a key finding from our experimental work is that end users seem happy to accept these new technologies as long as it is user transparent. So the key thing when we develop these control technologies is to try and reduce the interaction required by the end users to a minimum. But the biggest question really is, there is a lot of financial support required to take this to the next level. And there is also a lot of, or some significant regulation relaxing required in order to allow more and more networks to operate in this fashion and receive the benefits of community energy. Okay, so that's presentation concluded. So I'm happy to take questions if I can answer them.
Thank you very much, Professor Sumner, for your very interesting presentation. It gives a very clear view of the future challenges for the electricity grids in communities, but also many opportunities. We have some questions to you from the audience. The first question said, you showed how big community requires less batteries storage, but for higher power systems, it is possible to reduce the necessity of energy storage in the future by using auxiliary services integrated in renewable generation?
Yes, I think if I understand the question correctly, we can get benefits from using demand shifting. So, for example, one of the demand shifting is by incorporating the electrification of heating and using that as a big demand shift. So we can trade off. We don't always have to invest in battery systems if there are other elements that we can use for load shifting or for energy storage. So electrification of heating or air conditioning, for that matter, provides us with a good load shifting capability. Refrigeration networks allow us to do that as well. So demand side management is really being used now in supermarkets, for example, in the control of some of the big refrigeration networks that they have for storing food. So I guess if you can have a mixed community where you have shops or you have places where there's air conditioning, as well as having domestic residences, if you can exploit the different loading profiles of each of these, then you can probably reduce your infrastructure costs, the battery costs, even further. I don't know if that helps to answer the question or not.
Yes, I think so. Thank you very much. And we have two questions about electric vehicles. The first set, your results show that the electric vehicle charging can be a big load at time where no energy is available. How will be the impact in 10 years where electromobility becomes massive? And the other question about electromobility said, hi, for energy communities, does the electric vehicle batteries any impact into the power system, considering that those are plugged at night?
Yeah, so let's go back to. So the Trent Basin project has some work incorporating electric vehicles and chargers into the system. And the idea here is to look at several different aspects. So one is to try and reduce the number of vehicles. So rather than replace every conventional vehicle with an electric vehicle, if you can design a community to make better use of pool vehicles, shared vehicles, then that is one way to reduce the future electric loading. I think although it is from a consumer point of view desirable to have an electricity infrastructure that can cope with replacing every petrol vehicle with an electric vehicle, it's not feasible. And to be honest, it's not necessary. Most car journeys are quite short within the UK. So the idea of having car pools is quite reasonable. Now, going back to when I incorporated it or when we incorporated it, within the loading systems of our first community, here we had quite a crude mechanism for load shifting. So we allowed the consumer to program a maximum delay that they would allow within their system. And it just so happened with our community, we set all of the delays the same. But we could certainly stagger this reconnection of electric vehicles back onto the grid to make this less impactful on the overnight electricity consumption. And we assumed that all of the cars were being used to their maximum capability every day. Whereas I think once we fully understand electric vehicle usage, we will see that electric vehicles do not need charging every day, maybe every 4 or 5 days. So we just need to be a bit cleverer in how we create the charging systems, regulations, if you like, how you can get reward by not charging every day, for example. I hope that answers the question.
Yes, absolutely. Thank you. We have a more specific question. Is there an optimal size for the community considering the battery size and controller complexity?
That's a very good question, because for this work, I think, sorry, next slide, isn't it? For this work, we went up to 70. I don't think you get any improvement beyond 70. I guess we're now starting to get into the complexities of very complex communication systems. But I think with the approach that we used of having a central hierarchical controller that has a very, very slow update time, and then controllers within the household that do the fast work, I think that means that the limiting factor is not the control system. I think the limiting factor here is probably the communication structure. But even then, with internet communications as they are, and with 5G and 6G being researched now, the communication infrastructure is probably sufficient to allow you to go up to thousands of houses if possible. I mean, that's what people are talking about here, certainly. as long as you have some degree of local control within the house. It doesn't need to be particularly intelligent, but you just need some small degree of local control. So the smart meter maybe needs to have a little bit of a microcontroller with it and some communication to control local equipment.
Thank you. Other specific question about this problem is, what time scales do you consider for solving the two-layer control problem?
Well, we've looked at several actually. We've brought it down to 15 minutes, which is a good compromise between allowing the low level to work with a 1 minute sample time. And 15 minutes allows us to have a reasonably sized community here. So we've gone up to 30 dwellings with the model predictive control. Obviously, the complexity or the size of your community will then increase the complexity of your optimization problem. So to be honest, we've not looked at going to community sizes much more than 30, but 15 minutes for what we're doing seems plenty at the moment. And I guess you can always throw cloud computing at it to try and get better performance value out of your calculation platform.
Okay, thank you. A question more about the implementation, the real implementation. What strategies are you considering to promote load shifting in local industry of Nottingham?
Sorry, load shifting in local industry?
Exactly, in Nottingham.
Okay, that's an interesting question. We have a business development unit within the University of Nottingham. So anybody who is interested in trying to improve energy consumption within their business can contact our local business unit. And we discuss the usual strategies, the standard strategies of just improving equipment that they have. For example, putting in double glazing or removing any old lighting and replacing it with LED lighting. But we also do talk about the potential for moving towards electric vehicles for transport. And then if they're still interested, we do talk about the new technologies of perhaps doing some demand side management locally, because there is equipment out there associated with certain electricity suppliers who will allow you to do this automatically as long as you go with that particular electricity supplier. So we can't really do anything innovative with many of the companies because because the regulations I was talking about don't allow us to, but we can help advise them, go to the network operator to get some experience of these technologies through the generation companies, the electricity suppliers who do have these capabilities for demand side management. So the short answer is we try to encourage them in every energy saving technique, and load shifting is one of them. So we point them in the direction of that.
Perfect, thank you. And we have another question about the storage. Fuel cells can be a solution to storage problems in microgrids, or the batteries are better in that matter?
I think in terms of the application that we have, fuel cells are a very expensive technology. Sorry, I should have said we have tried fuel cells. Unfortunately, I don't think we have a picture. I forgot that. So within this community that we employed this battery, well, this is the power converter. It had a 15 kilowatt hour battery. We also had a fuel cell, and the fuel cell was, I guess the building was about the size of the room I'm in at the moment. So, it's a standard size small bedroom. So the whole room was that size, and it contained the storage for the hydrogen and the fuel cell. And the hydrogen was only capable of delivering half a kilowatt, 500 watts. So it was a massive infrastructure for the power that it could deliver. And I understand that, that size will come down and that the cost will come down. But I think the bigger problem was that it was response time was so slow. And I think for that community, we were able to use thermal storage in terms of energy shifting, load shifting, to do the job that the hydrogen was doing. So when we're looking at domestic applications, I think hydrogen is not going to work. But hydrogen will work for all sorts of other applications. And I think you're looking for applications where you need a lot of energy storage and the power fluctuation from it is relatively flat. So maybe it accompanies a battery, or it may be accompanies something else that has a faster response. But the hydrogen provides the baseline, if you like. And I think there are a lot of good industrial applications out there. Potentially, if you have a big enough community, then it could be used within that, but maybe not at the moment.
Thank you. Very interesting. The other question is, in your opinion, which is the main challenge to implement distributed generation and BESS in a large-scale manner?
That's an interesting question. I think the two main challenges are the cost and the regulations. So the distributed generation has really expanded because single households have taken it up. Certainly in the noughties and the tens, it was individuals taking it up because of the feed-in tariffs or other reasons. But if they want to maximize use by having a battery, then the best way to do that is to work as a community. And at the moment, we're not allowed to do that. So finding a way to allow energy trading within the distribution system is the first thing to overcome. And I think we're making progress towards that in the UK, but it's very, very slow. And then the second challenge is, as always, it's the cost. I mean, I was talking earlier on about 10 or 11-year payback times for batteries, even when you're using it for a legitimate business like fast frequency response. For investors to take that as a serious investment, that payback time needs to come right down to 4 years if possible. So I think those are the two biggest advantages. The best, I guess the thing that's most encouraging is that people seem to be accepting these technologies and happy for them to be on the grid. There is a little bit of problem with people not liking wind farms. They're not very pretty in some rural areas. But on the whole, people accept renewable energy as part of the future of our energy system. So I think from a good point of view, getting people on board to help move this forward is something very positive, something that is happening well in the UK. And I think certainly within the young people as well, which is, obviously it is very important to them. So if they're enthused by renewable energy, then hopefully they can help move this progress forward.
Thank you. And we have the last question, which is, what do you think about a direct current in power system? We can see a rise in HVDC projects in transmission, some projects in microgrids and load switches data centers. But what happens in the distribution system? Do you think the future is more AC or DC? And I can add that the storage technology are also DC, right? The batteries and the fuel cells.
Yeah, I mean, in a lot of senses, it makes sense to go to DC because most things, one way or another, require DC as part of the power conversion process. And as someone who's power electronics engineer, you say, well, we want DC because it means more work for us, obviously. So it's beneficial to increase. But I think a realistic answer is the fact that AC is still cost effective for certainly transmission systems other than very long ones, and a lot of the majority of the distribution system, it's cost effective to use AC and good old-fashioned transformers. You have to have a very good reason to go to DC for everything, because it means ripping up, all of the cabling, replacing the transformers with power electronic converters, and there are a lot of benefits to that. I understand that, but the costs that go with it are absolutely massive. But having said that, if you take new build establishments, so if you're designing a new shopping mall or you're designing a new housing estate, maybe you could think of putting DC in there that connects to the AC grid via a power converter, and then get the benefits of both. And then it starts to proliferate. In this country, we have a lot of new build at the moment, and there is very little imagination in putting new technologies into it. They don't have standard solar panels on new build houses in this country, which is crazy. They don't have good insulation, which is crazy. They're not phasing out gas central heating, which is crazy. So if we could put in those technologies, then maybe with some of them we could find a home for DC and show that it is worthwhile and reliable. I think the key thing with DC is showing that it's reliable in the same way that AC is.
Thank you very much, Mark, for your time. Very interesting presentation and answers. It was a great opportunity to our students and researchers, and I'm sure will be an inspiration to new projects trying to solve the challenges in the future electric grids and community systems. And I take the opportunity to invite you to our second talk on Friday, September 3rd at 10:30 a.m. in Santiago, Chile time, to listen Professor Michael Merlin from the University of Edinburgh, who will talk about energy conversion and storage in high voltage systems. So thank you very much. Have a nice day and goodbye to everyone.
Thank you.